In the last couple of videos, we have been discussing pulse width modulations and talked about what it means and how the duty cycle controls the power. And then in the last video we talked about using the built-in PWM where you just set a couple of registers and that would control whatever pulse width you want to come out. The only problem is there's only one available for this particular chip. And sometime you may want to have different kind of flexibility or have multiple PWMs. So the question is there any way we could do that using the features that exist in most microprocessors? Yes, the answer to that question is yes. And in this video, what we're going to do is we're going to use a single timer, one of the 4 timers in PICmicro or whatever timer is available in particular processor you're working with. And we're going to use that, and we're going to use it to create a pulse width modulation, multiple or however many we need. Some compromises have to be made. Processor has to run at a higher speed to make sure that the frequency of PWM is high enough that the particular device you're trying to control doesn't jerk or doesn't have discrete features. Rather, it's going to smoothly run and smoothly average things out. For example, for a motor, as we've talked about, that is 20 times a second. So we're going to start this as general as we can, and then maybe use it to show that you can build multiple PWMs even if no hardware PWM is available. But we're going to do some simplification for ourselves just to make sure that we don't overload our processor. So one is, for most devices, rather than having 0 to 100 be a continuous time, for this example, what we're going to assume is that we're only interested in setting the output at 0% power or 10% power or 20%. So we're going to in intervals of 10, and we want to be able to go between 0 and 100%. And let's assume that we want to be able to have at least we want our frequency to be at least 100 hertz. Okay, which means that my period, which is 1 over f, is going to be roughly 10 milliseconds. Okay, and so if I allow 0%, 10%, and all that, that basically means that if I want to have let's do so I will have if this is the time, and we will have, and let's say 0 time is here, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then back to 0, 10. So if we make this our cycle, if we say our cycle is from here all the way to here is t, and let's say these are in millisecond, then I have a period of 10 millisecond. And if I had a timer that interrupted me every millisecond, then I would be ready to take action at any given point in time during the cycle. So let's say I have a count, let's call it the cycle count, and let's say the cycle count, and I have a timer, and my timer interrupts every 1 millisecond, so I'll increment the count, and that would be the 1, 2, 3, 4, 9. When I reach 9 and going to 10, instead of saying 10, I will start 0 and count again. So at every cycle, I would have counts 0 through 9 in that cycle. So what that allows me to do, so for example, I could have another variable called PWM1, and whenever the count is less than this value, then I will set it high. When it's not less than, I'll set it low. So for example, let's say we set it to 3, and that would give us what I'm claiming, that would give us a 30% cycle. So let's see what happens. So if it's 3, I'm going to, using my rule, as long as it's less than that, it's going to be high. When I get here, it's going to go low, and then come to here. At this point, it's going to go high. When it reaches a 3, it's going to go back down and run. So now all of a sudden, I have a 30% duty cycle. Okay? So that's all I have to implement. I have to have a timer that ticks off at every 1 millisecond, and I have to have a variable called PWM1, which 1 says 10%, 2 says 20%, 3 says 30%, and then I have to have a variable count, which counts 0, 1, 2, 3, 4, 5. And then later on, if I want to have another variable called PWM2, let's say that's my second PWM, and it's set at 5 instead of setting at 2, then instead of going low here, the second one would go low at 5, and I would get a 50% duty cycle. Now let's go take a look to see how would we implement this using PICmicro and the capability that it has. For this one, again, a lot of these are pretty straightforward stuff we've done before. This portion is just doing the overall configuration of our particular processor, including all the SFR and bits and all that, defining a couple of locations to carry the variables of count. That was the cycle count, which goes 0 through 9, starting at the beginning of the cycle, stopping at the end. PWM1 would be the first PWM we want to implement. PW2 could be the second implement. And then if you want more, you can set to more, more of them as you need to do that. And the rest here is the code that would go ahead and support the PWM that we've talked about. And it looks like these PWM1, the PWM duty cycle for the first one is whatever number you put in PWM1, that times 10. So if you put a 7 in there, it's going to give you 70% duty cycle. If you put a 3 in here or 5 in here, it gives you 50% duty cycle. Okay, the rest of this should be familiar to you as well. Org 0 is the reset vector, so when the system is turned on or resetted, we'll jump to this location, which will execute this piece of code. So let's go take a look at what initialization will we do. Well, a couple of things. We are clearing the variables we have. So when this is done, C count will have a 7 in it. PWM, I'm sorry, C count is cleared, so it's have a 0. PW1 will have a 7 in it, and PWM2 will have a 3 in it. And then down here is basically what we've always been doing. This is assuming we have a EDBOD that we are writing this code for, so there's a bunch of I/O directions that are predefined based on what the EDBOD uses, and that's basically setting the I/O directions. One thing we gotta do in here, we gotta set the speed a little bit higher. Since we want the timer to interrupt every 1 millisecond, we gotta make sure the T oscillator is much higher than what we are used to in the previous videos. We've always talked about 32 microsecond. In here, we're gonna set the oscillator to 40 megahertz, which basically means that the period for each oscillator clock would be 1/4 microseconds. So that's the one difference that we are doing, and this is set of instruction. The 6 making the bits 1 in this particular way gives us that. Then what we are doing here is we are kind of setting up timer 0 to interrupts us every 1 millisecond. 1 millisecond is 1,000 microsecond. So let's see what we're doing. We're putting 42, so we are disabling the timer. It's always a good idea to disable the timer. Timer 0. And then we're setting it to 8-bit. I've done a little work beforehand, so I know I really don't need the high and the low, so I'm going to set it to 8-bit to make my life easier. And I've decided that the pre-scale of 8 is good enough for it. So what does that mean? That means duration of the tick is going to be 4 times the T oscillator times the pre-scale. So it's going to be 4 times a core, fourth, which is the cycle, times 8, which is 8 microseconds. So each tick is 8 microseconds. I want an interrupt every 1 millisecond or 1,000 microseconds. So number of tick would be 1,000 divided by 8, which gives me 125, which a hex value would be 75. Now I know that I'm not going to use the high byte. There is really no reason to use the high byte because the count is only 125. And then I'm going to use the low one, and so since I've set it to 8-bit, once the count comes up to 100, interrupt happens as our count is incrementing into 100. So if I want to know how many counts I want to do, I went ahead, one of these should be different. So we could put a 17C in here and subtract that and get 71 or 72 out of here. Okay, so that will tell us how many counts we need. And then let's go ahead and go back here and take a look at move LDEV. So we will take that value and put it in timer 0. Let me go back and do a little calculation before we go on. It looked like I made a bit of a mistake here. 125 in hex is actually 7D, and then if you subtract 100, 70 from 100, you will get an 83. So 83 should be really what we are going to put in timer 0 low, and that will give us 1 millisecond later, because it's got to count up 125 times before an interrupt happens. Up to now, we've set the timer, but now we got to go enable the interrupt. So here it says set the bit on timer 0 interrupt enable on, clear the flag, turn on timer 0, and make sure the flag is clear, and then enable the global interrupts that we normally do. And right now we are sitting in a loop here doing nothing. Well, all that's going to happen in exactly 1 milliseconds later, there's going to be an interrupt that happens. And since we set the interrupt priority, since we cleared the interrupt priority, that means it's going to be a low priority, which means this is going to jump to low priority location, which is this. As you notice, I have not talked about high priority. As a matter of fact, we are not really using high priority. I went ahead and put high priority here. If you notice, location 8 jumps to high priority, but high priority does nothing. It should never happen. Low priority, first thing we do, we turn the timer off, and then the next thing we're going to do is we're going to go ahead and take a look to see where the timer is. So as we said, the count starts at 0, and so if it comes in here, checks the count. If the PWM is less than the count, then it's going to turn it on. If it's more than the count, it's turning it off. So basically what it's doing is setting the high time. It's going to be high, count is 0 is high, until count is less than PWM, then it goes low. So whatever you put in PWM 1 is going to control RB3. So yes, RB3. And then when it's done, it's going to branch off to this, and it's going to be done. And once the PWM is equal to the count, or its count is higher than PWM, then you're going to turn it off. Okay, so what's going to happen is that what comes out of RB3 is basically going to be a pulse that is doing one of these, and the period is always going to be 10 milliseconds the way we set it, but this portion is going to be whatever PWM 1 has in it, millisecond, and that ratio is the percentage. Now we have a second one, PWM 2 is exactly the same as that, except is using whatever we put in PWM 2 to control it. Like just to be safe, we set when we started the whole thing, we set PWM1 to 7 and PWM2 to 3, which basically says what comes out of this one is going to be 70% power, and what will come out of RB4, because PWM2 is 3, is going to be 30% comes out of RB4. Because this does exactly the same set of sequence we did with the first one, except what it's doing is going to be comparing PW count to PWM2. As long as count is less than PWM2, it's going to turn it on. When count becomes equal or greater, it's going to shut it down. And that's it. And then at the end, we increment the count. Remember, the count has got to go 0, 1, 2, 3. And when a count is equal to 10, we're going to clear it to 0. So count only can go 0 to 9, and then restarts again. And of course, remember, there was an error in here, so we got this is 83 to get us another second later. Another millisecond later, get an interrupt. Then we come back, we turn the timer 0 on, we clear the flag, and we return the interrupt. And since the main part of the code is really not doing anything, all we're going to be doing is waiting until the next millisecond when an interrupt happens. In this particular case, I only set up 2 pulse width modulation. There's really no reason you couldn't have a third or a fourth or a fifth one if you need it for a particular application you're doing using the same technique, just copy and pasting and changing to PWM3 and create a third variable called PWM3 and on and on. That brings us to the end of this particular the use of timers, which is using timer 0 in this case to build 2 PWM, one running at 30%, one running at 70%. So, so we're using the timer interrupt to figure out when we turn this on or turn this off. That does it for this video.